Welcome back to MA 211. Let's go ahead and get started with the course. So this is a course on differential equations. Let's go ahead and define what we're talking about. A differential equation is an equation involving a derivative of the unknown function. Now, I've got some things in italics and bold here, and obviously those are important. The most important thing to notice here is that the unknown that we're looking for is a function. It's not a number. When you're in a differential equations class, your number is not going to be, or your solution is not going to be the number 3. Your solution will be a function. A function is something like t squared plus 8, right? So we're looking for a function. We are not looking for a number. And one subtle point is it's okay to have solutions that are constant functions. So it's okay to have something like y of t is constantly 3. That is a function. That's okay. But it's a function. It's not a number that we're looking for. Okay, so let's take a look at some examples of differential equations. So, for example, we might want to find a function y such that dy dt plus y is equal to the constant function 14. So in this example, the unknown is y, and we're taking a derivative with respect to t, so its independent variable must be t. So again, I'm looking for something like t squared plus 4 or e to the t or something like that. Okay, so in this problem, I want a function y such that y squared plus y prime is equal to the function that is y's second derivative. So again, the unknown, it's y of something. I used the prime notation, so I didn't really name the independent variable. So I'll just put a dot there. It's y of something. Here, the unknown is the function x, and it's a function of some variable, probably t, but whatever, I use the prime notation again. So once again, I don't really know the name of the independent variable. And here we see the unknown function is u, and you see that I've taken the equation says partial of u with respect to x plus partial of u with respect to y. So u is a function of x and of y. So you can have the unknown function might have one variable, it might have lots of variables. It just depends on what the equation tells you. Now, really, right, this symbol here, I should really write y of t, right? Because this thing is denoting a function, and it's a function of t. So it would be better if in the equation I wrote y of t here, and I should really be writing dy dt at the point t right there, but no one ever does that, so I'm not going to do it either. If you take a differential equations class anywhere, everyone's too lazy to write the independent variable there. So it would be nice if people would write that, but they don't, so neither will we. Okay, so that's what a differential equation is. It says find a function such that, you know, y plus a derivative of y is equal to something else. Okay. So now there's a subtle point here about this equal sign that's sitting right here and right here and right here and right here. These are equal signs between functions. We'd like two functions to be equal. Here I would like the function that I get from adding x double prime and x prime to be equal to the function that is constantly 0. So I'd like to know what equality means between two functions. Now here's a fairly formal definition. Two functions, f and g, are equal on the interval a to b if and only if for every x between a and b, f of x equals g of x. So this is an equality between numbers because f of x and g of x, those are going to be numbers. So what we need is for every x in this interval, f of x to be equal to g of x. So what's that mean sort of graphically? That means what? If we were to plot f over here, and it looked like that, and we were to plot g, and it looked maybe like this, okay? Maybe they're different for a while, and then on some interval they're the same, and then they're different for a while, okay? Function equality depends on the interval where I'm asking for about the equality. So between these 2 points, say 1 and 2, f of x may well equal g of x on the interval 1 to 2. However, if we look over here, say at -1 to say 4, it's clear that f and g are not the same on the interval -1 to 4. So function equality depends totally about the interval that we're talking about. Okay? So let me just mark that out here. So in this example, f equals g on the interval 1 to 2, but f is not equal to g on the interval -1 to 4. Okay? And the reason is because of these regions. Okay? So I'm going to give you some examples. Right after I read the example, there will be a little box that pops up. When the box pops up, the video will stop. You'll have to click the box to get the video to continue. So when I ask the question, I want you to think about the question for a little bit, answer it yourself, and then click the box and see what's going on. So if f is cosine squared x plus sine squared x, and g is the function 1, is f of x equal to g of x on 0 to 2 pi? Well, let's go ahead and graph things. So I put some axes here, right? We can go ahead and simplify things. If I were to graph, let me choose a color here. Oops. So if I were to graph f of x, I would get constantly 1, right? Because we know that for any x, cosine squared x plus sine squared x is actually 1. So here's f of x. Here's g of x. Let's plot it in a different color. And they are identically the same, right? It doesn't matter what x I plug into f, I get 1. And it doesn't matter what x I plug into g, I get 1. And so they are the same. Okay, let's try another one. If f is the square root of x squared and g of x is x, are they the same on 0 to infinity? All right, well, let's go ahead and plot the square root of x squared. And it should just be your nature to say, well, that's just x, right? That's correct if x is positive, right? So here's a graph of f of x for between 0 and infinity. But what happens if you plug a negative number into f? If you plug in, say, -5 to f, -5 squared is 25, and the square root of 25 is 5. So the graph of square root of x squared, this is actually the absolute value of x, right? So that's what f of x looks like. Now, what's the graph of g of x look like? Well, g of x is the function x, and it looks like this. Okay, so let's look. Between 0 and infinity, so ... infinity is over here, yeah, we can see that g of x is actually equal to f of x. So f does equal g on the interval 0 to infinity. So for a lot of numbers, they're the same. What if I ask about the interval -1 to 1, though? You can see that between, here's -1, here's 1, we can see that between -1 and 1, f is not equal to g, right? Over here, there are places where f is not equal to g. So f is not equal to g on -1 to 1. So they're not the same. So we see that asking about when two functions are the same, that depends a lot on the interval that we're talking about. What about one that's perhaps more subtle yet? If f of x is, this should be a 2 here, sorry. If f of x is 2x over x and g of x is just the function that's constantly 2, are they the same on the interval 1 to 2? Let's go ahead and plot g of x first. So here's 2, g of x is constantly 2, so it doesn't matter what x I plug in, I get that straight line right there. That's a heck of a nice straight line, if I do say so myself. Okay, let's go ahead and plot f of x. Now, you should just by nature want to say 2x over x, that's 2. But is that correct? Well, certainly for lots of x's that's correct. But what about at x equals 0? At x equals 0, f of x is not defined, right? So f of x is not defined at x equals 0, and so certainly g is defined at x equals 0, f is not. Now, what about on the interval 1 to 2, which is what I was asking about? Between 1 and 2, these two are absolutely the same function, right? They are absolutely the same between x equals 1 and x equals 2. So f is equal to g on the interval 1 to 2. On the other hand, what if I ask about the interval -5 to 5? Okay, between -5 and 5, there is this one lone point at x equals 0 where f and g are not the same. So f is not equal to g on the interval -5 to 5. Okay, so now we have an idea of what function equality means. If I say that two functions are equal on a given interval, that means at every point in the interval, the two functions are the same. If there's even one point in the interval where they're different, then the functions are not the same. Now remember, when we have a differential equation, this y is a function, and so dy dt is a function, so this whole side here, this is going to be a function. Oops, sorry, I'm erasing. Here we are. All right, and a function's not equal to a number. This is a constant function over here. And so this equal sign is function equality. All right, and the differential equation, or saying solve dy dt plus y equals 14, what's that mean? That means find me a function, y of t, such that dy dt plus y is equal to the constant function 14. And you should be asking yourself, on what interval? If you ask me if two functions are the same, you have to tell me what interval we're talking about. Now, in ODE, or in differential equations, we never say what interval I'm talking about. We always just mean find y of t such that dy dt is, or dy dt plus y is equal to 14 on the largest possible interval. So find me the biggest possible interval where dy dt plus y is 14. Okay. So here's a question for you. Here's a differential equation, dy dt plus y equals 14. Is e to the negative t plus 14, is that a solution to the ODE? Take a minute to think about it. Can we check if they're the same? We just have to calculate. We have to calculate dy dt. That's going to be negative e to the negative t. We have to calculate y of t. that was given to us. That was e to the negative t plus 14. And now we want to know, is dy dt plus y of t equal to function 14? And we can see that, yeah, look, you take dy dt, you add it to y of t, you clearly get 14, since dy dt plus y of t, that's negative e to the negative t plus e to the negative t plus 14, that's 14. It's certainly a solution to the ODE. Now the question is, on what interval is it a solution? And we can see that, well, it doesn't matter what t you put in here, you'll definitely get 14 out. There are no weird undefined points or anything like that. So it's a solution on the interval negative infinity to infinity. All right, let's try another one. Is t to the 1/3 a solution to y squared times y prime equals 1/3? And if so, on what interval? Well, let's go ahead and calculate. Let's see. Y squared, that is going to be, sorry, I hit my pen again. That's going to be t to the 2/3 power. Y prime, that would be 1/3 t to the negative 2/3. And so, y squared y prime is going to be equal to t to the 2/3 times 1/3 times t to the negative 2/3. Okay. Now notice that y prime here is the 1/3 t to the negative 2/3, and y prime is not defined at t equals 0. Okay? And so this whole expression, y squared times y prime, is not defined at time t equals 0. So y squared times y prime, that's not defined. Okay? Now the function that is constantly 1/3, that's certainly defined at time t equals 0. And so y squared times y prime, that's not 1/3 at t equals 0. Okay, so this thing, 1/3 or t to the 1/3, that is certainly a solution to the differential equation on some intervals, but it's not a solution to the differential equation on any interval that includes time 0. So what we would usually say here is y of t equals t to the 1/3. That is a solution on negative infinity to 0 and on 0 to infinity, but it's not a solution at time 0. All right, and that's it.